right, natural disaster students, welcome back. Quick review here of dam failures, and kind of goes along with floods, even though they're one sort of natural disaster. Floods, dams are intrinsically sort of man-made failures, but they certainly can result in floods. So I think it's important for us to talk about them here in a natural disasters class. So to start with, some basics about dams, just in terms of some of their pieces and parts and some of the forces acting on a dam. This is the Oroville Dam in Northern California, the largest dam in the United States. The dam itself is that barrier that stops the flow of water, or controls the flow of the water, better way to put it. The reservoir is the body of water behind it. Reservoir, sort of by definition, is an artificial body of water. It's man-made, as opposed to a lake, which is naturally occurring. We have an outflow here at the bottom, which is a series of pipes that are used to control the water level in the reservoir, and then again how much water you let out here into the river that goes below the dam. This particular dam also has a hydroelectric power station, so you generate electricity from that. That's not uncommon with dams at all. And then you have a spillway, which is this little channel here that's used as sort of a backup emergency way to control the water level, to make sure that the water level never goes up, over, and down the face of the dam. You do that, that's typically catastrophic and leads to failure. Let's then look at the, one more thing too, forgot. On here is we have what's called the left abutment and the right abutment of the dam. And the left abutment is basically, if you're standing on the dam, the left abutment is on your left-hand side, the right abutment is on your right-hand side. So this is my right-hand side, this is my left-hand side. I know it's reversed for you guys, but so this would be the left abutment of the dam, this would be the right abutment of the dam. And it's just where the dam goes into the valley wall. And sort of that boundary between the land and the dam itself on the sides. All right. Another thing we want to talk about in terms of just terminology about dams is how we measure the water in the reservoir. The volume of water, or I should say the unit that we use is what's called an acre-foot of water. This is the amount of water that would be on 1 acre of land if it was flooded 1 foot deep. That would be 1 acre-foot of water. For perspective on that, an acre of land is about 44,000 square feet. That's roughly the size of a football field. Flood that 1 foot of water, that's roughly 1 acre-foot of water. And just for perspective on that, that's about enough water to supply 3 to 6 households, depending on where they're at. Central Valley, probably about 2 households. They use a lot more water in the Central Valley. Households do. It's crazy how much they waste. Here in Southern California, we probably get 6 or 7 households out of that. So we conserve water a lot more than the Central Valley does. All right, why dams are built, pretty straightforward. Again, variety of reasons here. I'll kind of skip over this. What I want to look at are the forces acting on a dam. The most important thing is the water depth. The depth of the water really dictates the amount of pressure that exerts on the dam. And this is something that you probably realized if you've ever been in a swimming pool and you dive deep in the swimming pool, and you know as you go down towards the bottom of the swimming pool, you feel more pressure on your ears. Well, same thing with the dam. As you go deeper and deeper, you get more and more pressure, water pressure as you go down. And the arrows here represent the pressure, and the longer the arrow, the more pressure you have acting on the dam. And so the height of the water then dictates how much pressure is on the dam. And so it really is the height of the reservoir that is critical to understanding the design of the dam that you need. The volume of the water back here really isn't that much of an issue in terms of design of the dam. Volume of the water becomes a problem if the dam fails, but as far as the volume here is really not the critical part. It's the height that is the most important part. So, all right. So, other things. The water uplift. This water that we have in the reservoir is under a tremendous amount of pressure. And not only is it pushing on the dam in this direction, it's also getting into the ground and coming up underneath the dam, creating what's called uplift. So in essence, what water's trying to do is water's trying to push the dam this way, but also lift it up. You kind of combine those, really what the water's trying to do is really it's trying to kind of tip the dam over, which is one of the reasons why dams are so wide at their base. Part of it is because that's the area of maximum pressure, but you also need a good foothold to resist that uplift movement as well. Another force acting on the dam is the weight of the dam itself. Dams are heavy. Dare I say that they are dam heavy. And so you have then the weight of the dam itself you have to factor into your calculations. Dams, because they are very heavy, they have to support their own weight. They will eventually kind of settle into the ground a bit, and you have to make sure again that it's able to withstand those forces, the weight of the dam itself. Other things you have to factor in: seismic loading on dams. Dams are often built in mountainous areas, and mountainous areas are areas that often get earthquakes. So you have the shaking that adds to the stress of the dam, back and forth, up and down. Settling, like I mentioned, the weight of the dam will cause the dam to sink into the ground slightly. So you just have to account for that. Most dams do that, but you have to account for that settling and make sure that it settles evenly. If you don't settle it evenly, it could end up, again, settling unevenly and then tilting somehow, which again would be catastrophic if it did that. So a variety of things that can act on a dam. It sounds scary perhaps, but all you have to do is just account for these and then engineer around them. That's what engineers do, and they're very good at that. But you have to account for all these different forces, again, acting on your dam. Now, next thing I want to get into are the types of dams, and we can classify dams largely based on the materials that they are made of. So we have basically concrete dams, and then we're going to have what we call fill dams, ones that are made from fill material, basically earth material. And then we're going to have another one called an inflatable dam. So concrete dams, large amount of concrete. I'll kind of blow through this pretty quick. This is just, again, a large amount of concrete here, the concrete gravity dam. Then we have an arch or buttress dam. I do want to just take a second to explain how these work. This uses the architectural concept of an arch or buttress to help distribute load, or the force acting on the dam. And arches and buttresses have been used for thousands of years in architecture to do this in various types of buildings, as well as dams. We've used this in modern day dams quite extensively. And the reason you do this is because it makes it much more efficient way to build a dam. Basically, you can use less material and save money, but having the same amount of strength in your dam by using an arch or buttress, or in some cases both. So here's an example of an arch in a structure, in an aqueduct. And so the weight, of course, is going down, and what these arches do is they end up distributing the weight of this onto these pillars here. So rather than having to have this whole area filled in to support the weight of this building, you can just have it go down onto these pillars, and then you end up with these nice open spaces in between. So that's essentially what an arch does. If you take that arch concept but flip it horizontally, that's essentially the same thing you can do with the dam. It allows you, again, to take the force of the water and exert it along the arch itself and into the canyon walls. I'm going to show you that in just a second. Here's a buttress. Buttress sort of does a similar thing. Here, the wall of this church is trying to push outward, and the buttress is pushing against it, holding it in place. Again, another way you can simply just distribute the force into a different area. Notre Dame, a good example of that. So dams do the same thing. Here we have the Hoover Dam outside of Las Vegas. The water, as we've talked about, again, is largely pushed this way against the dam. And then what the arch is going to do is going to take that force and distribute it basically into the canyon walls along the right and left abutments. And so it allows you to build then a very tall, massive structure with a minimal amount of material. And that allows you to basically save money and build even a larger dam for the same amount of money. So it's a very efficient way to look at dam construction. This is an example of what's called a multiple arch and buttress dam. This is the one up at Big Bear. If you've ever been to Big Bear, you know Big Bear Lake is up there, beautiful lake. I love Big Bear. But it's a reservoir. It's technically not a natural lake. It's a reservoir. And it's this dam here on the sort of western end of the lake that creates the lake itself, the reservoir. And it is, you have these multiple arches here and then these buttresses here. Essentially what happens is the water pushes on the dam and it distributes that weight along the arch and then into the buttress and into the ground. So you get to build that dam with a minimal amount of material. So it's an interesting dam structure, one of my favorite here in Southern California. So, all right, so fast forward through that. What I want to get to next is looking at fill and embankment dams. So concrete dams made out of concrete, fill or embankment dams are made out of basically dirt material, earth material, and we have a variety of types of fill dams. And again, they're fairly common. Now, I do want to mention too that the design of concrete dams and fill dams is very, very different. Here's a typical concrete dam here in terms of cross-section versus a typical fill dam. The fill dam is going to have more of a trapezoid kind of shape, and a concrete dam is going to typically have more of a triangular kind of shape. Very, very different. You can't have earth material with a vertical back like you do with a concrete dam, because it will simply slide away. So very, very different types of designs, and actually, frankly, they fail typically for very different reasons as well. So, all right, so let me jump through a bunch of this and just some examples of line dams. This is just an inflatable dam. I want to mention this real quick. Inflatable dams are made out of rubber. Typically, and the advantage of an inflatable dam is you can have it inflated when you want it and need it, and then you can deflate it when you don't need it. So it's a temporary structure, usually only 5 or 6 feet tall. They're usually not very big, but we have several around here. This is actually where the gold line goes over the San Gabriel River in Azusa, right near Azusa, Doherty area. And again, you can see it inflated and then deflated. So you have those dams as well. All right, so the failure of dams. Dams fail for very different reasons. And again, sometimes it's often dependent on the type of material that's being used, but design error, construction error, poor location is a big problem. The geology, underlying geology isn't good. There's faults in the area, mass wasting can occur, operational errors. Dams need to be operated. They can't just build one and walk away from it. Extreme rainfall is always that worst rainfall event that you don't anticipate. So they do fail for a variety of different reasons. And it's usually very complex reasons, and it's rarely just one reason. There's usually 3 or 4 things that happened all at the same time. You take one of those out, it doesn't fail. You put all 3 or 4 together, and you have a dam failure. And like I said, concrete and fill dams, they fail typically for very different reasons when they do fail. Now, one I want to mention real quick is just the Orville Dam. This went through a problem back about 3 years ago, February 2017. And what happened here was the spillway had a problem. The spillway started to break apart over here. And the dam itself was fine, but if the spillway failed, it would have been still pretty problematic. So they evacuated nearly 200,000 people downstream until they could get the water level lowered in the reservoir and trying to make it as safe as they could. But you might remember that just came about 3 years ago when I was going through some problems there. This is spillway there. There's an emergency spillway, and both of them had problems. You can see here water getting out of the main spillway, and then the secondary emergency spillway was also about to fail. So fortunately, it didn't fail, but it was a very tense couple of weeks there as they were trying to get the water in the reservoir down to a safe level. So they've since fixed the problem, but still an interesting example of a problem, at least at a dam, not necessarily a dam failure. But let me jump ahead a little bit and look at one of our dams, and that is the St. Francis Dam. St. Francis Dam is up near Santa Clarita, and this dam failed catastrophically. And as you can see here, and for perspective on this picture here, here's the dam. This is about a 200-foot tall dam. This little figure right here, that's a person for scale on that. Another one here, you can see the people here in the foreground and this huge tall piece of the dam that was left. And it broke apart on either side of it. The origins of this dam failure are quite complex, but let me see, this image here kind of shows it reasonably well. There were several problems with this dam. The primary one was simply where it was built. It was built into rock material that was not sufficiently strong to have water ponded up behind it in a reservoir. And you can actually see these sort of crescent shapes here. These are actually mass wasting events. And what we believe happened was a landslide occurred on the left abutment that started to pinch in on the dam and caused the dam to tilt forward. And that put so much stress on the dam that the dam eventually just burst. And it burst right around midnight on March 12th/13th. We don't know the exact time at which it failed, but it was right around midnight. So you'll sometimes see this listed as failing on March 12th, sometimes on March 13th, just depending on which source you're looking at. But it was built by William Mulholland, failed in 1923. Mulholland had built 2 dams in his life, and the previous one was this one here called the Weed Canyon Dam, which is a carbon copy of it, which is just south of the Hollywood sign. So Mulholland had a big problem because he had 2 dams that were built the exact same way. One failed. The other one didn't fail, but it's not at full capacity even to this day. It's kept at a much lower level because it's not as safe. Teton Dam failure, real quick on this one. This one was in basically kind of south-central Idaho, on the west side of the Teton Mountains. It was completed in 1976, an earth dam, 305 feet tall, massive structure. And basically the reason for this failure was the material in which the dam was built. This is the actual dam site here. This is the remnants of the dam the part that didn't fail. It failed on the right abutment. And when you look at the rock in the right abutment, you can just, even on this photograph here, you can see all these cracks in the rock. And the problem was water got into those cracks, got around the dam, got into the dam from the side, which it wasn't supposed to, and started to carry pieces of dirt out with it, and ultimately led to the failure of the dam itself. So they never got the dam was basically almost brand new when it failed. It had only been operating at full capacity for maybe a month or 2 before it failed. So certainly an example of a bad dam location. So anyway, that's a bit about dam failures. I know it's kind of quick, but just hitting the highlights there. So any questions, let me know. Otherwise, I'll see you next time. Until then, stay safe.